Take the numbers 2, 3, 5, 7, and 11. These are the indivisible atoms of mathematics. Every other whole number in existence is built simply by multiplying these primes together. When you plot them on a standard number line, their placement looks like static. There is no obvious rhythm. They appear as discrete points scattered across a one-dimensional path. Sometimes they appear back-to-back as twin primes, like 11 and 13. Other times, you'll find yourself staring across massive numerical deserts with no primes in sight. Relying on this linear perspective forces us to treat prime gaps as chaotic noise. This creates a mathematical stall point, an analytic failure that stops us from writing a formula to predict the next prime. But that chaos might not belong to the primes themselves. It is likely an illusion created by the restrictive, one-dimensional space we force them to occupy. To find the true underlying pattern, we have to escape the flat line and evaluate the sequence in a higher dimensional space. To test this, we drop the primes into the complex polar plane. Instead of a line, we use a grid that functions like a radar screen, requiring two variables, a distance and an angle. Rule 1 controls distance. We plot a prime using the reciprocal of the gap preceding it. A massive prime desert yields a tiny fraction, forcefully culling that point toward the origin. Conversely, a tight gap aggressively pushes points to the far perimeter. Rule 2 determines the angle. We multiply the prime by the irrational golden ratio, ensuring each point sits on a unique part of the circle. This dispersant prevents predictable spokes, guaranteeing every prime finds a non-overlapping coordinate. Mapping thousands of primes resolves the chaos into an organized structure, a dense central disk packed with high-frequency gaps surrounded by a sparse outer ring. This geometric organization isn't just a 2D snapshot. The framework scales as the sequence grows. The triggers for this scaling are Fibonacci primes, numbers like 5 and 13, which act as developmental milestones. Every time the sequence hits one of these milestones, it resets its algebraic base, jumping from base 3 to 6 and then to 12. This shift in counting logic requires more coordinate axes to distribute the numbers evenly. To maintain that even distribution, the math forces the 2D prime map to fold upward into 3D cubes and eventually 4D hyperspheres. Primes function as the immutable mathematical skeleton, the structural anchors that allow this multi-dimensional routing geometry to converge and stabilize. This theoretical geometry translates directly to a physical engineering challenge, bypassing the memory wall in high-speed computing. Standard networks rely on flat 2D Cartesian grids. As traffic grows, linear data vectors move towards centralized nodes, leading to inevitable intersections and data packet collisions. To resolve this, the R4 prime router replaces hardware-dependent state locks with topological coordination. The R4 utilizes a hex-hive modulo 6 topology, mapping physical hardware interfaces exclusively onto the prime coordinates we visualized earlier. By locking parallel transport channels to distinct primes within the same residue class, the system ensures paths never naturally intersect. Hop's angular routing then guides data across this curved space, bending channels past each other. This prime-aligned addressing creates a collision-free substrate, allowing the system to sustain 1.2 terabits per second, a throughput that standard clock speeds and flat geometries cannot reach. By escaping the one-dimensional number line, we find that the perceived chaos of primes is actually the rigid structural order required to coordinate high-dimensional data.